Fun. I am. Hi, everyone. We're recording. So, you guys figured this was coming, and if you knew enough about calculus, you know that the opposite of differentiation is probably a bigger portion of the course than just differentiation. So what we're kind of going to start with is given, and I'm just going to example, f of x is equal to 6x cubed. N antiderivative of little f of x is, so we use the notation f prime and f double prime to go one direction. To go the other direction, we use, just sometimes, not a lot, we use a capital letter. An antiderivative of little f of x is big f of x, such that the derivative of big f of x is little f of x. So that's one little point I'm going to make. We're going to use the word antiderivative for all of about 3 days, and then we'll never use the word antiderivative ever again. The word that is used more commonly than antiderivative is integral. However, antiderivative and integral have different contexts. And we'll kind of see that here in a second. Because there exists, sorry, I always want to use these math symbols like this one, which means there exists. Because if I start to introduce these bit by bit, then by the end of the year I can use a lot of symbols instead of these words. So there exists an infinite number of antiderivatives for f of x. So every function has an infinite number of antiderivatives. So let's return back to the f of x is equal to 6x cubed. Can you give me one possible f of x, one possible big f of x? 6/4 x to the 4th power. Can we simplify 6/4? 3 halves. How'd you do that, Ricardo?
Work backwards.
You did. So instead of multiplying by the exponent and then subtracting 1, what you did, hopefully, is you raised the exponent by 1 and then divided. So what I kind of did with the 6x cubed, I said, all right, this is going to be 6x to the 3 plus 1. And then we're going to take that 3 plus 1 and divide by the 3 plus 1. That's the process. You'll get used to it. Say pimento. Ricardo, can you give me another possible capital F of x that would give me the same derivative? Once you realize the change, you'll be able to get an infinite number of them. Right? Now do you see why there are an infinite number of them? The general one is to say f of x is equal to 3 halves x to the 4th plus c, which represents a constant. Because what's the derivative of a constant? 0. Physics people, that constant can be thought of as an initial condition. And your initial condition is not ever dependent on your rate of change or anything. So that's going to come down. So we kind of talk about this right here. That's a name, not just it's not just an antiderivative. This is called an indefinite integral. Because it's the form of all possible functions whose derivative is little f of x. So let's actually formally define some things in sort of a middle school math way where they put the defin on one side. My middle school teachers did this all the time. Definition. A function f is an antiderivative of little f on an interval I if f prime of x is equal to f of x for all x in that interval. That's just formalizing our definition of this. f1 of x equals 3/2 x squared plus root 2 is an antiderivative of little f of x is equal to 6x cubed. f2 of x is equal to 3/2 x to the 4th plus x is not. Let's slide this to the left. Do you see why not? Yeah, the derivative of x is 1. So this derivative would be a 6x cubed plus 1, and that's not the same as 6x cubed. Okay, next step, theorem. Given capital F is an antiderivative of little f on the interval, capital G is an antiderivative of little f. Means the same thing, so I'm going to say if and only if capital G of x is equal to capital F of x plus a constant. What this is saying is quite simply, if you have two antiderivatives of the same function, they differ only by some constant value. We don't really formally talk about that a lot. But when we do this, that constant is going to be excruciatingly important. So I want you to look at C right now and see the C as lots and lots of little minus ones. Just see the minus ones pop up all over the place, because forgetting each C value is a minus 1. And so in a test where you do lots and lots of integration and you forget the C everywhere, this can destroy you. Don't let it. Don't let it do that. You must remember the C, because the only way that I have to really push that on you is to do lots of minus ones here and there. Then you will not make that mistake ever again. So, number 1, if y prime is equal to 3x, find y. I'm going to pause the video for a second to at least let our Beck. What's y equals? 3/2 x squared. So I just write it like that because it's simple. How many of you guys put your plus c just now? If you didn't, put a minus 1. You just lost a point. I'm trying to push that. So it's so easy to forget, and you saw that and yay. But what? Because it's asking for the y, any y value. Specifically, if you don't put the plus c, you're saying that that was plus 0, but you don't know that. You don't know what that constant was. So you have to put it something like a variable down, identifying that. Now, I want to dissect. Sorry, go ahead, Kayla.
You can't say that it's just you can just put any number in.
Nope. You want to put a variable that represents it could be any number. Y prime, as you guys remember, was this, right? dy dx, change in y with respect to change in x. And if I say that's equal to 3x, We've also seen where we can, well, a couple of times, I can actually split this up a little bit. I could multiply both sides by dx to get dy is equal to 3dx. Remember your related rates? Where I could divide both sides by t if I wanted to and make it dy dt is equal to 3x dx dt. But we're going to do something a little bit different here. I'm going to insert a symbol that you may or may not have seen before. This symbol. This symbol is the integral symbol. And what it means is do something. It's the opposite of this operation, which means take a derivative with respect to x. d dx of 6x squared is 12x. When I do an integral, instead of doing the d of that, the derivative, I do the this of this. And so if I want to integrate something, what I actually need to do is I'm also integrating with respect to a variable. You take the derivative with respect to a variable. You take the integral with respect to a variable. So the integral is paired with an infinite little, we're going to call an integrand, like a little infinite change. And I get the integral of 12x. And I can go backwards. That would be 6x squared. Say it. Plus c. So this dx right here, I'm going to change colors because that actually pairs with the integral. They're paired. You can't have one without the other. And the dy here on the left is also paired with its integral. And the 3x is the function itself. Yes?
Where do you get that 6x squared?
The integral of 12x right here.
Oh, is that a different problem?
This was like going backwards now.
Oh.
So the integral of dy would be what? Well, let me kind of separate this out now. Let's put a function in there. The integral of 1 dy. If I'm integrating 1 with respect to y, what do I get? What's the function whose derivative is 1? But if I'm doing it with y's, then it's y. And on the right side, the integral of 3x is 3 halves x squared. And we do the plus c. Strictly speaking, what you actually did was you added a c to both sides, and they're different c's. But if I take this and subtract this from both sides, can't I just call that another constant? Something minus something else? That's kind of what we're doing, and I'm just saying y is equal to 3 halves x squared plus c. I had a question years ago about why I put a c on one side but not on both. And it's like, well, they're different constants, so I'd have to put them with subscripts. And as soon as you move one to the other, you just get a different c value. Yeah?
Why does it look as though we found the derivative of dy, but the antiderivative of 3x?
We didn't find the derivative of dy. We did find the integral of dy. So if I went backwards and I said, all right, now let's take the derivative of both sides. The derivative of y is dy. And the derivative of x squared is, or 3x would be 3x dx. And I'd have that. And then if I just divided both sides by dx, I would get a classic looking integral of y prime equals. So no, we did go integral on both sides. I also want you guys to think of this as opposites. So you guys know that plus and minus are each other's opposites. Multiply, divide are each other's opposites. If I go raised to the second versus square root are each other's opposites. I can go raised to the n and nth root are each other's opposites. You guys know a lot of other opposites like sine and arc sine. You know e to the and the natural log of something are each other's opposites. You know that b to the and a log base b are each other's opposites. These are all opposite operations that you guys have learned. I could replace sine and arcsine with cosine and tangent. You know all those. This is another operation. It's an operation done on an entire function. d dx versus the integral with respect to x. Those are opposites. They go in opposite directions. Does that make sense? How everything here is an opposite of some sort. Don't worry, there are additional operations to learn as well. Okay, we're going to do another example now. The integral of 8x dx. And I'm going to use each of these to specify a rule that will make life easier. This rule is the constant multiplier rule. It's the same constant multiplier rule that we dealt with back with derivatives. So what I'm actually going to do is I'm going to pull the 8 out. Whether you do that in your head or whether you actually rewrite it, I'm fine with either. People won't really usually rewrite it, but if there's a complicated thing that you're taking the integral of, we usually pull out all the constants because we don't want to deal with them. So you're really left with the integral of x, which is, now that's the derivative of x. X squared over 2. The over 2 is going to throw you off sometimes. And then let's not forget, and then we would simplify this, 4x squared plus c. Most of the time, you're going to go directly from here to here. That's fine. But I do want you to kind of appreciate and see a little bit what the thing is. Now, I'm going to make one little modification here. Strictly speaking, this is actually what we did. We pulled the 8 out, and I had this. And when I distributed the 8, I get this. But 8c is really just 8 times a constant, which is another constant. This is poor math here because I'm actually saying 8c and c are the same thing. So what I tend to do, and we'll do this from time to time, is go back and rewrite history by making this be a c1. So it was actually different. So that my final one could be the one with the c, and the ones before I just kind of start to put some numbers back in. Okay, next one. The integral of 1 over x to the 5th dx. You will also sometimes see that as the integral of dx over x to the 5th. You see why those are the same thing? When you were doing derivatives, a lot of times you guys would rewrite the derivative in a convenient form. You're going to do the same thing here. I would suggest for the initial parts of this, and even for some of my BC kids, this is much of what they do a lot because it's just easier to perceive it this way. They rewrite it x to the negative 5 dx. So I'm going to show this because this can be tricky. We're going to take x to the negative 5. You're going to add 1 and then divide it by negative 5 plus 1. And then we're never going to forget the plus c because you know immediately that has to come after. This gives me x to the negative 4 over negative 4. Or probably expressed better as negative 1 over 4 x to the 4th plus c. Number 4. I am going to pause the video and give you guys a chance to do this one. Okay, resuming video. I rewrote this as x to the 1/3. For the first bits, if you want to write this as x to the 1/3 plus 1 divided by 1/3 plus 1 plus c, that can give you kind of a fewer steps to do in your head. X to the 1/3 plus 1 is x to the 4/3. And divided by 4/3 is the same as times 3/4. So that becomes 3x to the 4/3 over 4 plus c. I would leave it like that. You feasibly could also have that as x to the, or 3x to the, or cubed root of x over 4 plus c, but I like the exponent notation better, and I think you guys do too. Looks cleaner. Let's do some trig. Remember, the 3 can come out, so this is really the integral of sine x dx. And you're just basically saying, what's the function whose derivative is sine? Negative cosine. So you get negative 3 cosine x plus a constant. The integral of x cubed minus 4x squared plus 1. Please do not write it like this. I think you guys can all agree you need those parentheses to close off the polynomial. And just raise and start dividing. X cubed becomes x to the 4th over 4. 4x squared becomes 4x cubed over 3. 1 becomes x. And then you have plus a constant. Let's do a type of problem that I would argue is Kendall's favorite. 2x minus 1 over radical x dx. We talked a lot about rewriting these things in a particular way that makes it easier to take an integral or derivative of. Couldn't I write this as 2 root x minus 1 over root x using the distributive property to divide that out, which is the same as the integral of 2x to the 1/2 minus x to the negative 1/2. Again, this is the first day you've done integrals, so let's write the first one as 2x to the 1/2 plus 1 divided by 1/2 plus 1 minus x to the negative 1/2 plus 1 divided by negative 1/2 plus 1 plus a constant. Gives me 2x to the 3/2 over 3/2 minus x to the 1/2 over 1/2 plus c. And that's just 4x to the 3/2 over 3 minus 2x to the 1/2 plus c. You could write that in radical notation, not completely necessary. Last one. Sometimes you might need to do a little bit of substitution, some trig substitutions. If I were to break this up into sine x over cosine x times 1 over cosine x times dx, isn't this just the integral of tangent of x secant of x? And which function's derivative is tangent secant? Secant. Just basic secant. Of course you remember that. It is. You will get used to it. And you're going to get better at your derivatives because of all the work going forwards and backwards. We'll make it kind of a little bit clearer. Okay, this is not going to be due until after the test, but you might as well go ahead and write it down so you know what the assignment is that's linked to this. On the calendar, this extends all through the weekend and all through Monday. So if you look at the calendar on Monday, you'll see what it is. And then after the test or during the test, I'll write this on the board to remind you guys this is due the next period. So thank you.